So this is a simplified version of what was going on last week, or rather a cleaned up version of what was going on last week, with some stuff for the future. Oh yeah, okay. So, hey, go away. Good. All right. So, thing number one is this: if you're doing wave shaping, there are two kinds of ways that you could think of to do it. One is using an expression, that's to say, describing algebraically what you want the function to be, and the other way is just by throwing it in a nice function, throwing it in a nice function table like this. The good thing about the function table is that it takes a reasonable amount of compute time. That's to say, depending on what kind of interpolation style you want, it might just be looking up a pre-stored point in a function, or it might be doing that and then some algebra to do interpolation. If you do the expression, it could be as much computation as it takes to calculate the expression. So the table is really a way of pre-calculating the expression. The gotcha is that the table is only one thing. There's no way to parameterize it. It's just sitting there being a table. So that you have to sometimes think hard about how you're going to do things that are changeable in time. So the table is not something that you really want to change in a continuous way in time, because you would have to compute all the points of the table, and then it would even take the time to try to draw it again, and that would be kind of ugly. So a bad way to change something that you're doing by using a wavetable would be to just recompute the entire wavetable. Especially considering that if the table changes discontinuously, the sound changes discontinuously too, right? So that, for instance, here's a thing for putting something in a waveshaper. Let's get this network going so we can listen to it. And now, of course, next thing is I haven't managed to test sound, so let's see how we're doing here. No, we don't have sound. That could be because no, I only have one audio device. That could only be because I don't have the volume up. Oh, and that's full blast, so that can be a little bit louder. And any more than that, we got too much. Actually, that's too much. Ugh, sorry. There are ground loops in all these rooms between the projector and the audio, and the correct thing to do would be for me to get this thing going, but then I would probably have some other crash. I think I tried to do that last time, in fact. Okay, so now, so here is a, oh, that's what I thought the ground loop was. That's me. 50 hertz, just like in Europe, and one of you should have told me that we were in the wrong continent for that to be the buzz. There it is, really. All right, so what I really want to do is put some proper sound in there, or thing in here, so that we can enjoy it a little bit more, like that. Okay, so what are we doing now? I overthought this and prepared a whole bunch of stuff in my head, and then forgot that, of course, then it's going to be sitting on the patch. But here it is. Let me just tell you what's up and coming. The first thing is there are two flavors of tab read. There's tab read 4, which is I should just mouse point it actually. Tab read 4 is the tab read 4 is the one that does 4-point interpolation. And tab read is one that doesn't do any interpolation at all. And an easy way to hear the difference between those two is to... Oh, what I really should do is I should graph the output, and then you'd really see everything. Well, why don't we do that? So what I'm going to do is I'm going to make another table down here, and it's going to be called output or something. Whatever, how it's spelled. Something I can spell again. Out. All right? And now out is going to have a tab right to it so that I can look at it. There, and now we need a button to start it off. And now I'm going to start looking at what this thing looks like as a signal. Yeah, good. Okay, so what you get is, this is one of the transitions. So what's happening now is there's a 68 hertz sinusoid with amplitude 45. I haven't told you yet what the scaling is on this table, but in fact, part of what's happening here is we are taking this oscillator, which ranges from -1 to 1, and we're rescaling it so that it ranges from 0 to 400. And the way we do that is by multiplying by 200 so that it goes from -200 to 200, and then by biasing it by 200 so that it is from 0 to 400. And then we go into tab read for Shaper 1, and Shaper 1 is a table with 400 elements. Why 400? Just because that was going to be that's a reasonable size wave table. I'll tell you a little bit more about that later. That's table lookup lore as opposed to wave shaping lore. But there are ways of knowing how many points you might want in a wave table for a given amount of audio fidelity, which is stuff that you might care about. The easy way to test for audio fidelity is to play a very low tone and see if you hear grit. So here, let's make it, well, all right, let's go back to 60 hertz. So there's a tone, and this is now the, this is now the 4-point interpolated version, and now what I'll do is try to do the same thing over here. Oh, I don't need to copy this whole thing because we're just comparing tab read versions. So why don't I be smart and do it this way? All right, and actually I can't tell the difference between that sound and this sound. Oh, hey, yeah, there's a difference. I didn't connect it quite the same way. Okay, there is a difference, and the difference will become apparent when I do this. Let's drop the frequency some more. And now let's do something else, which is to drop this. And now, hear that? That is the sound of non-interpolated table lookup. If I play you the interpolated one, you hear just the 10 hertz tone. And that's why we need this tab right. Here's the 10 hertz tone going up and down gently, very, very nicely and smoothly, at least as smoothly as I can graph, because I mean, you can only see it moving down 1 pixel at a time, I guess. Are you going to see this? You might not see this the way I'm doing it, because now if I start graphing the other one, it's going to be messed up, but it'll be messed up at exactly the same pixelation as is in the table. Oh no, I'm wrong. Look, you can see that it's being messed up. I need to catch it at the right moment. Well, I don't know, maybe that's a good moment to catch it. What's happening here that wasn't happening in the other place is that, okay, tab read tilde really just literally reads the value of the table out. Tab read 4 does a 4-point interpolation, which is to say it chooses the 4 neighboring points, the 4 points closest to wherever you are. And generally you'll be between 2 points, and so it makes sense to go 2 points to the left and 2 to the right. And then you just do something special if you happen to land right on a point. And then it draws a smooth curve, a cubic curve through those 4 points, and then the result is theoretically a much, much more accurate read of whatever continuous function it was that was in the table. And that works perfectly for continuous functions, and it works wrong for discontinuous functions. Here we have a nice continuous function. It's just a clipping function. You can call that a sigmoid if you want. And so what is coming out of here is, let's see, how can I make this more clear? I can't. So what's coming out of here is just literally what the sinusoid should be reading out of this. And so to see it clearly, I should give this a nice real frequency after I drop the amplitude. And now if I graph it, you'll see clip sinusoid, right? Here, right. And I think if I do it that way, you're going to see the same thing in both regimes. Okay, so what's happening here is this thing is being read out of this table, backwards here and then forwards here, and so on. And it's being read either either literally out of the table this time, which is to say exactly what point there is here, or in this case, it's the interpolated value. Now, the exact value, I know how to make this clear. Let's drop this a lot more, like to 0.1, so that we only get a very small amplitude, and then let's multiply it by 10 before we look at it. All right, so now what do we get? Oh, look at that! All right, now we found the way to really see the difference. That is different from this. Okay. So what these numbers are is points on this table. The thing is right now reaching forward and backward in a region that contains 4 points of the table. And so you see it actually move from point to point like this. Okay. This is what's known as bit crushing. And by the way, we have just designed ourselves a wonderful bit crusher by taking advantage of the what's the right word? By taking advantage of the limitation of a PD object. So this is bad programming style. I can show you maybe a more correct and readable way to do this later if you care to. In fact, I think I really should. Okay. All right. So this sounds like this, and this. And this sounds like this. Okay, so that's a clearly visible or clearly audible difference too, and you can even see in this thing why that should sound different. All right. Okay.
What about the indexing? For indexing tab read forward from 0 to 400 versus 1 to 400.
Oh. Yeah.
399 versus 1 to 400.
Okay. Yeah, I can. Yeah, let me give you a quick answer, but I'm not sure this will be totally comprehensible because, well, first off, as soon as I plug this thing in, who knows what's going to go wrong again. That table has 400 points, yeah. So here's maybe what you can consider as being a way of thinking about that. So I believe I'm in draw mode, and all right, I think I'm actually going to be able to do stuff here. Maybe. Okay, so function table with 4 points looks like this, maybe. Well, 4 points. And what a way to think of it is, well, this is the point that's at 0, and this is the one at 1, this is the one at 2, this is the one at 3. So 4-point interpolation would be drawing a continuous curve through these. And there it would make sense, for instance, to read a point anywhere starting at 1. So if I had a 4-point table, the points would be numbered 0, 1, 2, and 3. And doing a straight table lookup with no interpolation, as in tab read tilde shaper 1, like that it would be valid. Well, basically, if I gave it any number at all, it would truncate it down to the nearest integer. And if that integer were 0 or less, it would give me 0, and if it were 3 or above, it would give me 3. So in effect, the domain of that is from 0 to 4. Whereas the domain for doing interpolated lookup is from 1 to 2. Right. Or to put it another way, as soon as I exceed, if I'm at 3.5, if I say 3.5, the way the table lookup wants to do it is it'll truncate it down to 3, right? So all the way from 0 to 4, the function, the thing that I return is actually the correct thing in terms of this table. But if I gave it a negative number, it would wish for a number in the table, or a point in the table to the right, left. And if I gave it a number greater than 4, it would wish for something to the right. And so the natural interval over which the thing does its normal thing is from 0 to 4. And so here what you see is that there's 3 less. Is that right? Yeah. there are 3 points fewer that you can read. The segment over which this thing makes sense is 3 shorter. And that 3 is the same 3 as the difference between 4 and 1, which is the number of points that it's using. In other words, since you're doing 4-point interpolation, you lose 3 points. And what's weird is the points that you lose are first from 0 to 1 and then from 2 to 4. And this is confusing. There's simply no way not to get confused about this.
So you're saying anytime we use tab read 4 in this style, that we should avoid reading, we should add 1 to avoid?
Yeah, well, add 1 or just don't get below 1 or above n minus 2.
But doesn't PD automatically add points to the table for it?
No. What PD does is automatically truncate the input, or automatically limit the input to the domain that's actually possible given the number of points you asked for. The problem being it's the same table if you're doing tab read 4 or tab read. So in fact, it doesn't know when you make the table what style of reading and writing you're going to want to do with it. So it simply does literally what you ask for. Now, I've almost never seen situations where it makes an audible difference that you don't have those extra 4 points, but it does, but it's something that you can find on a sound editor. For instance, if you make a 1-second sample and use tab read 4 to read it, and you really should have 44,103 points and read from 1 to 44,101. Otherwise, you will see a little teeny blip where the thing sticks on the ends of the table. And you can find that in a sound editor, although it's rare that you would actually notice it. It's one of those things about computer music that you can easily not realize that your sound has these little imperfections in it, and later on you find out that there are imperfections in it, and that's what they were. The computer music repertoire is full of sounds with funny imperfections in it that were bugs that people only discovered later. Okay, so that's a little something about interpolating lookup. There are complicated formulas that tell you what the possible error is, but there's a very simple way of thinking about the error in the case that you're not truncating, which is that you're not interpolating, which is that the table really is like this. It's a stair-step function. And so there's an error in reading the function that is this area. And that area is proportional to the derivative, the slope of the thing. If the slope is 0, there's no error, but if there's slope, there is error. And furthermore, if you want this error to be down, say, 96 decibels from the strength of the signal, say, then what that means is you want this thing to be whatever, 2 to the 16th less in amplitude than the value of the table. And even say if you're storing something like a sinusoid, that ends up telling you that you need hundreds of thousands of points in the sinusoid to be able to make this thing actually be audibly good to 16 bits. That was interesting. All right, whatever. Okay. Oh, and of course this is what you hear. And in fact, if you look at this thing as this error thing is a triangle wave, and that triangle wave is exactly what I played you here. Let's see. When I was playing this very low frequency sinusoid, I'll play it even lower now. Oh wait, now I have to. Oops. Let's push this down. I have to give this now a larger value, like what? Oh, that's too low. I'm not doing the same. I haven't got it right. Oh, I'm using the wrong one. I'm sorry. That's the interpolated one. All right, now I can't make it misbehave anymore. There it is. So those sounds, that's this signal. And where you hear it, what's the right word? The place where it's quiet is when you're hitting the end of the sinusoid. When it's not moving, it's not giving you error, but then it's giving you error when it starts moving. Okay.
So peak of the trough, there's no
Yeah,
because it flattens out.
right. Because the sinusoid itself flattens out, so you're not moving anymore, so it goes away. Actually, if you listen to it, it actually loses pitch. It gets slower. And the reason it loses pitch is because if you're reading it less quickly, if you're toward the end of the sinusoid, you're going across fewer of these peaks per second, so the sound is going down in pitch. So this is not terribly audible when you push this up to a nice audible frequency. But it's there, and if you listen to it in a studio, you'll actually hear it. So that's a sound, and this is a sound with a little teeny bit of fritz on it. And you'll hear the fritz much more clearly if the pitch is changing than if it's stable, and all psychoacoustics will happen. Okay. All right. Now, the next matter that I want to talk about is getting stuff into the waveshaper, getting stuff into a wave-shaping function. And a way to do that is this. And I prepared this because I wanted to actually have a couple of waveshaper functions and wanted to look at what I was doing. The first thing is just these are all standard built-in PD objects except for for. There's no loop in PD. This is me making a for loop. You might want to make yourself a for loop because they're very useful, and there's no reason that PD had to make it as a primitive. You'll find out that everyone will want a slightly different version of this. Like, do you want to be able to bail in the middle of the loop, or do you want to, etc. There are all sorts of possible ways to make a for loop. And so you'll just have to discover which things you like in a for loop by making your own and discovering what it won't do for you and so on like that. 95% of the time when I'm doing stuff, because I'm doing things very simple-mindedly, I just want to count from number to number. And so this thing will give me, in sequence 0 through 399. And it will do it, what's the right term? There's a word for this. It'll do it atomically, in the sense that zero time will pass while the loop is running, so that you can actually squeeze one of these things in between two samples of output if you want to. It's instantaneous. And the way you make instantaneous loops is you use the wonderful until primitive. This is also a wonderful way to get in trouble, but you try it out and see how you get in trouble. You'll find out pretty soon what happens. Okay, and actually there's weird range adjustment stuff here that you probably don't need in your for loop. In fact, that I don't need terribly badly. So to put something into a table, what you do is use the tab right thing, which expects an index and then a value. And the index is just going to be the number from 0 to 200, and the value is going to be, and now we do exactly what we did here backwards. Okay, so what we want to do is we want to store tables, we want to evaluate some function on the range, in this case on the range from -2 to 2. Why -2 to 2? Just because that's what was working for me today. That would be a different number on a different day. It's arbitrary. -2 to 2 in... Okay, it's fine. The North Koreans are at us again. -2 to 2, here's a nice clipping function which goes from -1 to 1, and I just wanted to see the flat part at the ends. And I also wanted to be just dead sure that I actually had that extra point for doing interpolation. So why not just give myself a whole other unit of flatness? And the other thing is, the other function that I wanted to mess with is this nice hyperbolic tangent function, which never actually reaches 1, but it turns out that the hyperbolic tangent of 2 is so close to 1 that I couldn't hear the little kink here that happened when it moved off the edge of the table. So tables, sometimes if you're just going off to infinity, you want the table to stop at someplace finite, and wherever that someplace is should be far enough out that you'll either never hit it, or when you do, you'll have been so noisy getting there that you don't care that it has a little step, or that the step itself just be microscopically inaudible, which is, I think, what I ended up choosing here. The other cool clipping function that I've hit is not going to work so well, and that is the arc tangent, which only goes up roughly as 1 over n, as I recall. So it's going to not be as well behaved used as a table lookup function. So I'm just going to blow it off and just use hyperbolic tangent instead. because I don't know why. All right. So now what's happening is what we'll do is we'll make the thing have a logical value from -2 to 2. So the real value, the thing that's coming out of the 4, is going to be what goes into the tab right shaper 1. Sorry, into the index. That's the place in the table it's going to put it. But here, what we're going to do is evaluate a function on a number line, if you like, that will range from -2 to 2 as you sweep through the table. And so that number line we get this way. We take it and we subtract 200, which centers us around 0. And then we divide by 100, which makes it no longer go from -200 to 200, but now to go from -2 to 2. And this could have been divided by 200 to make it exactly the opposite of this. So here we multiply by 200 and add 200. Here I'm actually I'm making it twice as much. And then, all right, so, how about 3 different possible clipping functions? Okay, how am I going to make this smaller so I can get more of these on here? How about, I don't know. All right, this will be all right. I'm going to now do this, and then I'm going to duplicate it. This one will be a little shorter because here what I'm going to do is blow off the expression and just do the clipping. Oh, what did I just do? I miniaturized. Uh-oh, how am I ever going to get it back? There we go. Okay, so now this one does this. Ta-da. This is the thing I wanted to show. Well, I had to draw for you last time because I didn't have the wherewithal to throw things into the table so that you could see them. Now, this is a good example of when you don't put something in a wavetable, because 2 reasons. One is this is really just the clip function, and so why don't you just say clip instead of having all this garbage to look, or having all this garbage to look the thing up in the table. And indeed, last time when I was squaring and cubing signals, it was much, much smarter just to throw multiplies down than it was to throw the thing in the wavetable. Here, on the other hand, with hyperbolic cosine, you could run something at signal rate through an expr, but you really wouldn't want to do that a whole lot. That's making your computer work hard, and this is not anywhere, and looking it up in the table is a great deal less effort on your computer's part than running it through this expr. And now we're in great shape because we can actually listen to the result of tab read 4 fuzzing this sinusoid. Using this kind of shaper, or this kind of shaper, or this kind of shaper. And here, I can't tell the difference. Let me tell you what these are, I'm sorry. This one, this is a cubic polynomial, which is figured out so that its tangent, it's got a 0 slope at the bottom at the top, and it's -1 at -1, and it's +1 at +1. And if you actually showed more of that thing, it would wrap back around and do this kind of thing. But since I'm clipping, I'm only reading it through this portion of its cubicness, and so here you just get it at 1, which is the value it attains at 1. And how did I figure this out? I had to differentiate this thing and figure out how to make the derivative work out to 0 at positive and negative 1. I actually did it by trial and error first, and then I realized, no, I'll have to write this one down to get it right. And then it turned out to be a third. Okay, fine. Okay. And these, I had an interesting time actually trying to equalize these in the sense of getting them to have roughly the same spectrum, but I eventually found the way to get them equivalent sounding. And I think if you put a guitar through this, you're going to find out that this is a much nicer sound than that. But just with a sinusoid, I can't tell the difference at all. And this one has much worse behavior for high indices. It is much, let's see. It gives you, it might give you fold over because this thing is a this is a kink in the curve, and curves that have kinks in them have more high frequency content than curves that have continuous derivatives. And that's just a thing that I have to just sort of claim without giving you any good explanation of. So this thing will have high components that these two things won't. And you will hear the difference when you give this thing a very high pitch, but I don't want to mess with our ears right now, so I'm not going to bother with that. Actually, though, I do want to go back and get the nice. You're tired of being in the dark. I do want to get the. Can I do this? And can it actually read the stuff? All right. Oh, it doesn't. What couldn't it do? Oh, that's nothing. Oh, that's me. All right, sorry, I just got to check and see if I can make loops now. All right, so sorry about this. This is me trying to make an input to a fuzz thing. And now we're going to cut the oscillator out and do this. And listen to how awful that is. All right, that's this one. And now these, they're all awful. Okay. All right. I thought those were going to be not so awful as the clip, but all right. Let's find something that really sounds awful. That's pretty bad. And then there's this stuff. Maybe this will be all right. All right. Well, I'm sorry. I can't make it sound anywhere near as bad as I've been able to make it sound at home. I don't know. All right. So, what am I saying about that? I'll go back and next time I try to clip something and it sounds horrible, I'll try to figure out what made it sound horrible and bring it in. Right now I'm not able to make a bad clip, so I'm just so maybe you can just do the simplest possible thing and still be totally happy. While we're here, though, I want to show you the bias control on your amp, just to be a little bit more, just to sort of fill in something I didn't do terribly well last time. So I'm going to make another one of these. I can duplicate it and just add it to this. Just because this is something that people like on their amps, whoops, hey, dig. What am I doing wrong? Oh, these numbers are far too big, maybe. Yeah, let me do this. So this is. There's the too much bias sound. And a dedicated guitarist will just figure out the perfect combination of that thing and which pickup to give what amplitude to and so on to get just the guitar tone that they want. What that is doing is essentially sliding this, either, depending on how you think of it, it's either sliding that function to the left and to the right or sliding the signal to the left and right that you're using to read into the function. Okay. So that's kind of the end of that thing. Now what I want to do is talk about bit crushing as an example of wave shaping, because we actually sort of started doing bit crushing, but doing it through a wavetable is maybe not as smart as just doing it in its own right. And I think what I should do for that is save this and then make a new one so I can get rid of some stuff. So I'm going to save this and then do a save as, and it's now going to be 2. And now for this, we don't need the shaper anymore. I'll go back and get it later if I need it for something else. And I don't know, but these guitar chords might actually be just the perfect thing to bit crush, so let's hang on to that. Don't need any bias anymore. You definitely need an amplitude control. Now, okay, so how would you bit crush? Well, you just have to know the objects that do bit crushing, or you have to know the objects that do stuff. So an object that you want to know about is called wrap tilde. And so let me show you wrap tilde quickly. And in fact, the way I'll show you this is by throwing an oscillator through it. Is that a good idea? Yeah. All right. So oscillator. All right. Now we have tab right out. First off, let's not wrap it, and let's go look at what this thing looks like, and let's multiply it by too much, like 20. And it's reasonable speed, 200. There. Okay. Oscillator that's out. That's too big for the table. All right. Now I'm going to wrap it and show you what that looks like. Okay, this is useless for sound. Of course, it is a nonlinear function, so we can think of that as a waveshaper, but you really don't want to mess with this. That's just going to be ugly. Okay, that is this. Okay, well, you know, it looks a fright, but it is a periodic function. Periodic in, periodic out, so it has to be periodic. But of course, what it has is loads of discontinuity and everything else. Okay. The fun thing that you can do with wrap is rather than using an oscillator, use a phasor. So now here's a phasor that's too loud. Ta-da! There's a sawtooth that's going out of range, and now I'm going to wrap that. Yep. So it starts at 0 and then it goes up here, but since it wraps around, it goes that. Okay, so what wrap really is just takes whatever the number is, lops off whatever the integer part is, and gives you the rest. And importantly, if you give it a negative number, it doesn't tell you how far you have to go up to get to 0. It tells you how far you have to go down to get to the next integer, which might be -1. So minus 0.3 would give you positive 0.7 if you wrap. So what it really is taking the line on a number line on which everything can exist and wrapping it around into a unit circle. Circle of unit circumference, if you like. Right? Exactly like a tape measure. Okay? Now, my purpose in showing you that is to show you then, first off, now that we've got this sawtooth going in there, we should listen to it. Just because you want to have heard this. And that's interesting. Then you get this kind of stuff. And why do you get that? It's because, actually, let's do it 60. Every 0 to 6 sweep, it just sweeps 6 times, and so you get a frequency multiplier of 6. So all the integers, whoops, sorry. Okay. And then things in between are less well behaved. So if you do that, quickly once or twice before people can really hear how gritty and ugly a sound that is, you can get away with it, and it's a nice phasor sound. Okay. Okay. All right. So that's the wrap tilde object. My point to showing you that was to show you then what happens when you subtract the wrap tilde object from the original. Then you get the integer part. And so here, for instance, if I say, all right, we'll have an amplitude of 3. Okay, it goes from 0 to 3, but it wraps around from 0 to 1. And then if you subtract that from the original, then you get bit crushed sawtooth. Which, okay, now bit crushed sawtooth is not going to be terribly interesting because the sawtooth itself, what is there to crush? It's already buzz, and so you just get more buzz, right? But now, if you do that to something else, Well, you'll get nothing until the thing hits 1, and then you'll make it up to 1. Actually, let's sinusoid again. Okay, now what are we looking at? There's a sinusoid bit crushed, but it's way out of amplitude range. What we'd like to be able to do is have the bit crushing actually be within the reasonable audio range of the signal. So to do that, what we have to do is take the signal, multiply it by something obscene, and then do this wrap and minus, and then divide by the same thing. So let's do that. I'm gonna want 2 multipliers here, or am I? Not sure, but I'm gonna give myself 2 multipliers because here what I'm gonna do is whatever I do, I'm gonna multiply by a certain number, don't know what, and then I'm gonna divide by it after I'm done. Like that. Now this thing I'm gonna wrap like that. Okay, there it is. Okay, so there's now an oscillator, but now I'm going to give it a reasonable amplitude. So I'll divide by 100, say, so that we're just going from, let's do this. Okay. So now I have an oscillator which goes from amplitude 0 to 1, because I'm dividing the amplitude by 100. And now I can say, oh, well, let's multiply it by 1,000,000. Sorry. What have I done wrong? Oh, I'm listening to the wrong thing. That was a bad thing to have done, but a good thing. That would actually have been very bad if I had the amplifier set to a more optimistic setting. Okay, now I've got my nice sinusoid, and in fact, if I look at what it is, you can't tell any difference because what's happening here is I'm making the thing be of amplitude 1,000,000, and then I'm bit crushing it so that it loses the fractional part, so it only has integers. But the integers, since they are on a range from -1,000,000 to 1,000,000, there's 2,000,000 of them. And so it's good to apart in 2,000,000. We're not going to ever hear the problem. If you want to hear the problem, you set this to something that is small enough that you can actually hear the gradations. Oh, I don't hear anything yet. Oh, yeah, I do. Okay, so here's 1,000,000 again. And here's 100. And here's 10. And here's 5. And so actually this is continuously varying. And that, for instance, looks like this. And that looks like that. Okay, so notice that the more bits you give it, okay, this is called bit crushing because the original way of doing this, some earlier way of doing this would be to have a physical signal on a bunch of wires, which would be a binary number, and just drop the low order wires and keep the upper low order wires so that the thing lost bits. Or if you like, if you're operating in digital, if you're operating on a file, just drop the lower byte of the sound file you're in, just reduce it to 8 bits and then push it back up to 16 and play it, and you'll hear a nice 8-bit sound file. Okay, so making an 8-bit sound file is essentially quantizing the value of quantizing the voltage in the sound to the nearest of 256 possible values. So that is equivalent to taking the sound, multiplying it by 256, and then taking the integer part. Sorry, this ranges from -1 to 1, so actually I should have said 128 because it's from -128 to 128. So this is 1 byte of precision. And you can hear that, you can tell it was supposed to be a sinusoid, but you can also hear the grit. Yeah. Okay. And okay, so actual bit crushing is, reducing this value until you start getting what? Why don't I hear anything? What am I doing wrong? Oh, it's just too subtle. Okay. want subtle. All right, well, let's be unsubtle. The way to get unsubtle is to quit pumping it with a nice, well-behaved sinusoid and start pumping it with my nice guitar sound. Oh, and here we want to be able to... No, never mind. Yeah, let's have an amplitude control anyway. Hey. Okay, let's see what we got. First off, let's give it goodness. Smooth guitar sound, and now we say 10. Wow. No, something's wrong. There's no possible way. What the hell is going on? How can that be? Oh, you know what? This is very... The problem is I had the very, very high amplitude here. An amplitude much greater than 1. So if I just give it my straight ahead amplitude, now we've got... Yeah, there we go. Now we're seeing stuff like this and we're hearing proper bit crushing. Oh, that's interesting. It gets louder. That's reasonable because when you do this... Oh, yeah. Oh, so this is hovering around 0. So a thing will happen at some point. Yeah. What's happening is the bits get further and further away from each other, so at a certain point, it's really just, this is 1 bit. But 1 bit, as I drop it, is a bigger and bigger bit. So we don't change the amplitude at that point, we just make it louder and louder. And we have to get up a fair ways before you get more than 1 bit's worth like that. Hear a wah-wah effect there? There's some way to think about that. Oh yeah, if I did this, let's see. If I go back to the sinusoid now, I can make that wah-wah effect by just changing the amplitude of the sinusoid that I put in. So I don't know if you can hear that, but that's just me pushing the sinusoid up to a larger value. And what happens is there are more steps per cycle, and so it emphasizes different harmonics as it goes up and down. Okay. I think that's all I should tell you about bit crushing. Sorry, what was I going to inflict on you next after that? Oh yeah, a thing to, a thing to tell you about wave shaping is, of course, the sort of defining feature of it is that it's nonlinear, but it's nonlinear in the signal that goes in. It's actually linear as a function of the wavetable. So a thing that you can do, what's a good example of this? A good example of this might be going back to clipping. So let's, let's actually do a save as so I can. Linear. Okay, so the observation that I'm making, I guess, is a kind of simple one to the point of being a little too simple. Oh, let me just grab some stuff from the first one so that I don't have to build this all back. So I'm going to get this. Ooh, but okay, so let's get rid of some of this. All right, can I lose that? I'm not sure. I can lose that. Okay, let's So now, okay, so I'm going to give this, well, I'll just leave it, and then I'm going to make another one called Shaper 2. Oh, and I do want this because I'm going to put stuff in here, which, oh, actually, let's just put things like that. Let's see how we do. Oh, that's interesting. All right, whatever. Okay, and now what I want to try to do is, oh, I know. I'm just going to make a drawn wavetable. That'll be a better way of describing this. Okay, now I'm going to borrow this machinery here. And just run an oscillator into it, so I don't need that twice. And then I want to say Shaper 1 and Shaper 2. Maybe this is too trivial a point to be making, but if you do this, then you have a way of selectively giving yourself one sound or the other. And now, ta-da, you've got what Roland used to call vector synthesis, which is in fact just the idea that anytime you have more than one thing, you can just make linear superpositions of them. And then that gives you, if you like, a way of crossfading between the one and the other, or if you like, just an arbitrary higher dimensional set of possible timbres that you can have. This gets interesting when you start making, say, Chebyshev polynomials to build sinusoidal, to come up with harmonics of sounds. You can make combinations of Chebyshev polynomials that make combinations of the sinusoids, and you can either do it by putting the whole thing in one table, or you can do it by putting parts of it in separate tables and then crossfading the results, which is, of course, the crossfading itself is a computation that you have to do, but on the other hand, it means that the table itself doesn't have to be, you don't have to think of it as an immutable thing. If you can think of a family of tables that are linearly related, that are essentially all just combinations of simpler tables, just leave them in the simpler tables and then combine them at runtime. The example I wanted to make of that, I'm kind of chickening out of, which is clipping. What if you wanted to have something clip at? What if you wanted to be able to clip, but to have something have controllable volume? Arbitrary. What's the right way? When you clip something, then the volume that goes in is roughly the volume that goes out at low volumes, but at very loud volumes, the thing's clipping, so there's a sort of a limit to how loud you can make the thing. So you start losing dynamic range as you start clipping. Well, how would you make a clipping-ish function that allowed you to get louder as you made the signal that went in louder? Well, one possible answer is just clip it at different, have different functions that clip it at different ranges, and just add the results. So you're always clipping because the first one, at least as soon as you get past part of the first one, so that it can start clipping, you're already starting to distort. But then as it gets louder, a part that was linear then starts distorting, and so on. And that actually really, and here I'm going a little bit in circles because I could do that without actually having to have two tables. So I'm maybe being unnecessarily confusing about this. Here's this nice clip function that I can put in a table. What if I just decided that the thing that I wanted in there was, let's clip it like that, but then let's also clip it like this. Think, is that right? 50. And what about 202? So I'm going to add all this junk up. Ooh, yuck. I'm going to need a bigger trigger. Sorry, I'm giving you a PD lesson. I didn't intend to do this. Okay, let's do that. And then let's run it through this clip function. Hey. And then that clip function, and then that clip function, and then let's add them all up. This is ugly. Yeah, blah. This is why you shouldn't use PD to program. Oh, and then by the way, let's divide by 3. So that it'll fit in my nice table again. So now this is the sum of 3 different clipping functions. What am I doing wrong? Oh, there it is. Isn't that cool? And now, get my guitar out and start playing. Let's see, where do I want to put it? I want to put it right here. And lose the oscillator. And shaper 1. Oh, wait, let's turn this down. And now I can get, there's the first clip going. There's the second clip going. And there's maybe the third clip going, and so on. All right. I'm not sure this is a good practice, what I'm showing you here. Yeah, let's just leave it at that. At some point, you're going to say, well, yeah, but why indeed didn't I just go ahead and then undo this? And the answer is, well, no, because here you can see that the thing has actually got increasing, is actually increasing more. It doesn't just sort of hit the thing asymptotically necessarily. You can actually just keep on going up. I don't know, I'm not explaining that very well, so I just better stop trying to explain it. So at any rate, the point here is that you can make superpositions of things, and what you will get out is the superposition of the things separately acting on it. And the things that you could change would not just be the, say, if you're clipping, would just not just be the range of clipping, but also the bias. In other words, you could put clipping functions in various places on your left to right dial, and that would be just a continuously variable way of messing around with signals. Okay. Questions about all this? Okay. Yeah.
Why do you use the graph instead of just making it absolute, like abs tilde?
Abs tilde. Oh, I meant to talk about abs tilde actually. Well, it's a different thing.
But it's also reducing the resolution of the...
Well, sort of. Okay, so abs tilde does this. Okay, so going back to the sinusoid. Abs... Okay. Oops. Okay, let's see what we're looking at now. Oh, did I take away my... I need to get one of the... Where is it? Oh, I've lost the little tab rightism. I'll just make another one. Okay. Let's see, out. Okay. I actually meant to talk about absolute value as a possible shaping function because it's cool. Okay, let's do a save as. This is going to be 4. So here's the absolute value as a wave shaping function. Don't need any of that because we're just going to do a function now. The function is abs tilde. And, yep, there it is. Okay, so the original sound is here. So, it's one of those sounds that puts us up an octave. That's because the absolute value function is an even function. And anyway, here's what we're doing to the, ooh, yuck. It's big, yeah. Let's see. Why? Oh, yeah, look at that. My range is silly. Okay, there's a sound. Here's its absolute value. And there's what it looks like as a function. This has one really good property, which is exactly what I was working or trying to sort of see it. The thing that I was trying to claim you could sort of do with clipping, which is you could arrange clipping functions so that things kept on having kinks in it, but the overall volume change was, that at least in the large, you didn't have radical changes in gain from one gain range to another, right? That's also true of the absolute value, because the power that goes out is exactly equal to the power that goes in. So I can make the oscillator louder or softer, and I get no timbre change at all. Right? The only gotcha with this, so this is a really kind of cool function. The only problem with this is that it sounds lousy. If you now throw the guitar through it again, well, I don't know. Right now, all this distortion sounds exactly the same to me, so it actually doesn't. And I've heard absolute value do some really wretched things to a sound. One tiny thing about the absolute value as a clipping function is that it's always non-negative, and so there will always be a DC component, and so you will have to high-pass filter it before you do anything else with it. But then once you've done that, well, you've got yourself a nice, it can be loud and it can be soft, and it's always clipping kind of a thing. Right. It's not even just approximately true, it's exactly true that if you just scale the input, the output scales. But it's not linear, because it's not the case that if you added two things in, you would get the sum of the two things out. In fact, that's a good way to make it sound wretched. Let's go back and get two oscillators now. Of course, every time I say something's going to sound wretched, just because we have nice speakers or something, it refuses to sound wretched after all. I don't know. And that's this. Absolute value of sum of sinusoids. All right. So one thing, a general comment that I sort of made some reference to a little earlier. If things have discontinuous derivatives like this, they tend to have rather slowly sloping high frequencies. In fact, the partials go off as 1 over n squared in amplitude. If you have discontinuities in the transfer function, which will therefore make discontinuities in the sound that you hear out, then the partials will go off as 1 over n. And you will have trouble with foldover, and you will just need to be able to deal with foldovers in some way or another. One thing that I mean to tell you, as soon as we need it, we haven't really hit a bad foldover situation yet, so I haven't had to do something like this, but one can always make a sub-patch and run the sub-patch at some huge sample rate, and then filter and then downsample as a way of controlling foldover. And then you can get closer to the quality of an analog thing than you would have been able to otherwise. But on the other hand, if you're doing something with discontinuities, which is something that you frequently do in analog circuitry, like a sawtooth wave is kind of one of the basic things, or a square wave, that's one of the basic analog things. Well, those things are going off only as 1 over n, and that means that the, say, 100th harmonic, which is not a crazy harmonic to talk about. That's, if you're at 440, that is 44K1. That's what will feed back or fold right back down to low frequencies. That has about 1 in 10,000 amplitude, and that's audible. That's minus 80 dB compared to the original tone, and so that's already an estimable amount of foldover. That can be made to sound bad. And again, the higher the frequency, the higher the pitch of the thing that you put in, the worse that situation gets. So that's the thing that one wants to be able to control somehow. All right. The absolute value is interesting also because it's a lead into what I want to do for the second half of today, which is talk about the generalization of absolute value. The thing about absolute value is if you're stuck on a line, all you can do really is just fold it. But if you're sitting in a plane, then the absolute value is how far you are from the origin. And you can do something that maintains the absolute value but does all sorts of funky things to the actual value of the function. So absolute value, a thing about absolute value is that it exactly preserves the absolute value of the signal. The absolute value that goes in is the absolute value out. If -5 goes in, 5 comes out, but the absolute values of those two are the same. But absolute value is really the only non-trivial continuous function that will do that for you on the line, and that's because the line is an impoverished neighborhood, and if you make your way into spiffier neighborhoods, you can actually find much more interesting functions. Okay, and it is 6:30, even though it took forever to get off the ground. So here's a thing. There's an object in PD called Hilbert, whose thing is to do the what is not exactly a thing which is not exactly a Hilbert transform. The Hilbert transform is a mathematical abstraction that takes any function that you want and changes all the signs into cosines and all the cosines into minus sign. In other words, it takes everything and phase shifts it 90 degrees. That's not causal. You need to know the future in order to do that. But there are filter pairs in existence. In fact, here is one of them. We don't know where these numbers came from. But actually, I cribbed these numbers from a 4x patch a long time ago, and I asked the person who wrote the patch where the numbers came from, and he sort of was a little evasive. So I don't know. I think Tom has access to some literature that tells you how to get these numbers. So what the numbers do is they make filters that are phase shift filters, the difference of which is 90 degrees. So if I put a sinusoid in, now what I need to be able to do is graph two sinusoids that you can see the phase relationship between them, and there are two ways you might think of to do that. Let me do one. Let's do this. Let's put an array, and let's just say to put it, what am I really going to do? Sorry, I'm trying to decide whether to put it in the same table as this one or not. This has got 1,000 points in it. Okay, array. I can say put it in the last graph, and it'll have a size of 1,002, and it'll be array 2. Now there's a little bit of a, whoa! Is that a line, or is that array 2 doing that? That's really cool, but that's really not what I want. Okay, so let's not do that. And let's just do something normal. Put an array, and I will really just put it in a new graph. Good. Array 2. Come here. And now I want to have that have the same width as the other one, but I forgot what the width was. 800. All right. Now we can graph two things at once. And the only gotcha is that now we can't see any blackboard. And now what I'm going to do is start graphing stuff. So here's a sinusoid with unit amplitude. Good. And here is the output of one of the filters of Hilbert. Oh, but I want to do that on array 2. And I want the two to start at exactly the same time, so I'll hook them to the same button. And now I have, what did I do wrong? Oh, I'm writing it the same array. That's really, okay, good. So phase shifted sinusoid. Now the stupid thing is that that phase shift is just some phase shift or other, and if I give it a high frequency, it's one thing. It's like 180 degrees off, and if I give it very low frequency, it's almost nothing. And if it's somewhere in between, it sort of gets to be 90 degrees off. Who knows where? Oh, I have to be higher. Something like that. Okay, that's typical filter behavior. At DC, at zero frequency, there's no phase to be in except for in phase, or 180 degrees out, but actually it's really in phase with a negative amplitude. And at very high frequencies, frequently the phase lags by the number of, 90 degrees times the number of poles in the filter or something like that. So you get an increasing phase lag as the frequency goes up. A way to think about that is if you're pushing a kid in a swing set, the if you're making the kid move very slowly, much slower than the swing set's resonant frequency, then you're just pushing the kid and the kid goes forward, and you pull the kid and the kid comes back, and that's that. But then if you're actually letting them swing at the resonant frequency, you have to push them not when they are in the direction that you're pushing them, but at the bottom of the arc, right? So actually the kid swing trails the sinusoid by which you push the kid by 90 degrees. And then if you don't do this, but if you decide you're going to shake the kid like that, then you'll find out that the kid, where the kid is actually opposite where you're pushing it. So at very high frequencies, you get a phase inversion of 180 degrees. That's because the kid is a two-pole filter in this case. And this is, I'm being very sloppy about my description because actually the filter is changing. So really you need a mass on a spring to make all this correct, but it's still really quite true. Okay, so the phase shift in any kind of reasonable filter is a function of the frequency of the sinusoid that you pump it with. And the cool thing about the filters inside Hilbert is that they're amplitude preserving. They're all pass filters. So any sinusoid I put in, I'll get a sinusoid out with the same amplitude, and all that will happen is there will be some phase shift. Now what you do is you find someone who knows the numbers and get two of these things that have the property that whatever the phase shift is, one of them is about 90 degrees ahead of the other. So in sum total, I think the delay goes up to a half cycle for each of the two filters. Maybe it's more than that, I'm not dead sure, but maybe it's a half cycle, maybe it's actually 3 halves of a cycle. But at any rate, the deal is they both proceed from no drift to whatever their final drift is, but over most of the frequency range, one of them has gone ahead of the other and is staying about 90 degrees ahead of the other. And we can actually check that. Right now we're at 73 hertz, and array 2 is now 90 degrees ahead of array number 1 in phase. So it hits its peak right when array 1 is going through. And this will be true over most of the frequency range. Where it'll stop being true is at very low, stupid frequencies where you just couldn't do it because neither of them got off the ground yet. And so there'll be a point somewhere around 10 hertz, I think, where they finally, no, a little higher, where they finally actually make it up to about 90 degrees. That's higher than I thought. Yeah, something about there is close to 90 degrees, but I had to get up to almost an audible, or more than an audible frequency to get there. Doesn't matter. You just need this to be approximately true, and you need it to be close to true in most of the audible range. So here it's actually true, and then if I gave it, Nyquisty frequencies, then it would quit being true again, but then you wouldn't care so much about that either.
What did you change from before to make it so that they...
I changed what I was graphing. Originally I was graphing one of the filters against the input, and then I changed to just graphing the two filters against each other to show that their relationship to the input is just something unruly, but their relationship to each other is a pretty decently near constant 90 degrees throughout most of the audible frequency range. What's this good for? Well, it's just good. Another way of seeing what it is this picture here. What I'm doing now is I'm graphing 4 times a second these two same outputs, but instead of graphing them in time, I'm making a polar graph of them as if you had an oscilloscope with X and Y inputs and put the X and Y in, put the two signals in the X and Y inputs instead of having time be X. And now we'll see that actually if we go very slowly, like seriously slowly, like 1 hertz. Oh, that's bad. Well, okay, that's what that is. Actually, I don't know why that's happening. All right. What is happening? Oh, I'm sorry, it's aliasing with this. The thing is, it's exactly 4 times a second, so I'm hitting it at... so I need to make something like... I can change the pitch to numbers that are less well behaved, and then you'll see sort of what the thing's doing. So at very low frequencies, like nothing. There it is. All right, good. So now why is it going negative? This should be going this way because these two signals should be the same. So there's something wrong with the graphing here. One of these things got inverted somehow. And I'm not going to worry about that right now. Okay, so now the X and the Y signal are almost exactly the same. But at some point, as I start raising the frequency, you'll see that it starts going in an oval. Oh yeah, but I have to get more than a hertz or so. Yeah. My graphing is not really up to this. Okay, well anyway, now I'm moving it fast enough that you can sort of see a decent portion of the arc at each time. So now we're starting to get a phase difference between them. This is at 9 hertz. And I believe at 34-ish hertz where I was before, we get something that's close to a whole circle. Right. Not perfectly round. And below that, it's badly not round. But above that, it's progressively more and more nearly perfectly round. Well, that's interesting. Well, whatever. Just little graphing anomalies there that you should ignore because they're not really part of the signal. Okay. So this is getting two things that are 90 degrees out of phase. All right. Now, the thing about this is, at any given point in this cycle, you can actually measure exactly the amplitude, well, exactly to very close the amplitude of the oscillator, because the amplitude of the oscillator is just the distance from the origin to the point. So if I gave you a signal like this, then at some given point in the cycle, you wouldn't necessarily know what the amplitude was. And to find out what the amplitude was, you'd have to wait until you hit the end of the cycle, and then when you saw the slope change from negative to positive, then you would say, all right, that was a peak. Now I know what the amplitude is. If the amplitude is actually changing in time, then you would never know it, really, except right at a peak, maybe not even then. Here, you have you can just make a signal which is exactly equal to the amplitude, and the way you could do that is take the thing, take one of these signals and square it. Let's square both of them, just for the fun, and then graph those two things. Actually, you sort of know what's going to happen, because if I took this thing and squared it, and you saw that last time, this became a peak, and so on, then this will become a peak, and this will become a peak, and so on, and they will have alternating peaks. So, in fact, let's cut these. You'll see two signals, which, if you added those two signals up, would give you a constant, like this. There, I'm adding them up, and there's a little bit of not exactly roundness, but basically what's coming out is a constant, which is the amplitude of this oscillator. Actually, the squared amplitude of the oscillator. If I now set the amplitude here to 1/2, this goes down to 1/4. So really, if I want the amplitude and not the square of the amplitude, I have to take the square root of the thing. Like this. Oh, if you hook two things into the same input in PD, PD will add them for you. It's probably better style for me to use a plus to make it explicit. So now we have amplitude. So now, no matter what I do here, I've got a signal which is equal to the amplitude, which is equal to the amplitude that I'm putting into the oscillator. Sort of. I suspect if I go changing that at audio rates, there would be some lag in the measurement of the amplitude for various reasons that I would have to explain in terms of modulation. Like if I sinusoidally modulated the amplitude, really that would be adding other components, and then I would have to talk about beating effects. But nonetheless, if I put a nice clean sinusoid in, I get a nice clean amplitude signal out. Also, if I want to, I can figure out what the phase of this thing is. Okay, so let's go back to having a graph of the Let's go back to having a graph of the sinusoid that we're doing this to, so that you can marvel at how I could get this thing in and get this out. Right? Okay, so now what I'm going to do is see if I can get a hold of the phase. Now, phase is equally nasty because for any given, even if I knew the amplitude of this thing, which I do if I've done that part, still, if I tell you what the value of the sinusoid is, there are in general two possible values of the phase. Right? So I would regard this as being the same phase. Let's see. I would regard that as being the same phase as that because they're a cycle apart. But that's a different phase from here. Right? So how would I actually get the phase? Well, again, since I have the point, let's see, if I look at this point here, it only visits each point in the circle once per cycle. And so the phase is actually uniquely determined, even though it's not uniquely determined here. And what is it? Well, there's a form, or it's trig. The phase should be an angle which goes from 0 up to 2 pi radians, or 1 cycle, depending on units. Maybe if you're doing computer music, cycles is more convenient than radians. So it'll go from 0 cycles to 1 cycle and then repeat. In fact, it should be a sawtooth wave, a phasor in computer music language. And the way you get it is, well, it's the angle, and there's a triangle, and the whatever you call it, the opposite leg is the vertical axis, and the near leg is the horizontal axis, and mumble, you take the arctangent, right? So you do this. You say arctangent. Actually, you want the fancy arctangent. And I never remember which. Oh, there is none. There should have been one of these. Oh, maybe that's an PD extended. Never mind. All right. What I do is I take the arctangent this way. Since I don't like doing trig, since I was raised on DSPs that didn't have trig functions, here's computing the modulus. Those of you who codes DSPs, I will tell you how this all works if you're curious. And here's how to take the arctangent. So first off, you're going to fix the modulus. All right, so this is taking the square root and dividing it out so that you get a point which is on the unit circle from the point which is on whatever circle it was on. And then if you've got a point on the unit circle, you can take the unit circle and fold it, or just imagine it's a circle written on a piece of paper. Just fold it into quarters so that you get one quadrant of it. And then the arctangent is approximately a simple function of x and y. I think it's like approximately y minus x times something. In fact, I decided to do better than that. I thought of a cubic polynomial that roughly does it. And I don't know where I got that from. I just used a couple pieces of paper and figured out a good function. And then unfold the piece of paper again, and then there it is. This is angle divided by 2 pi. And it's just trig. So so this abstraction unit polar, which, by the way, where do you get this? You have to download SMEC, which is my guitar patch. I think it's the only place where I've actually got a copy of this where people can get it. And this thing has outputs which are the modulus, that's to say the radius, and the angle. So there's the, what? That should range from 0 to 1, and it's ranging from a half to, oh, that's because I've got this thing going. There. All right, so there's a nice phase. It's not graphing it terribly well, but it's a perfectly good phase. It's going from 0 to 1, and this thing is a rock-solid amplitude estimate of this sinusoid. Now that you've done that, you can turn that thing into anything that you want. So there are two ways of saying what's going on here. One is, as long as you preserve this, you can do anything that you want to this, and it will preserve the amplitude of what goes out. So you'll have a nice Ruley function whose output amplitude is simply related to its input amplitude. Okay, that's way number one of thinking about it. Way number two of thinking about it is this. Suppose I wanted any waveform at all. So let's drop the frequency so you can see this happen. Okay, so now there are, 4-ish cycles per, oh well, you get the idea. All right, so now I'm going to make another table and just draw something arbitrary in it. All right, since I've been talking about interpolation, I'll do the whole interpolation thing. Points, okay, all good. And let's do something that you can sort of see the form of. So let's make it, just sort of two humps with different heights, right? Yeah, good enough. Actually, way different heights, like that. All right. Now, what I want to do is make a thing which is this waveform driven by this oscillator. Why? Because this oscillator, I want to do this by wave shaping instead of just by oscillating this thing, because I want this to be possible to drive from some external oscillator. Okay. So what would I do? Well, okay, so you've seen it. So we're going to need a tab read for Let's see. First off, I'll just make an oscillator without driving it by this thing. So to do that, we need a phasor. And I'll give it the same frequency so we don't get too confused. And now, if I want this phasor to read this thing as a waveform, by the way, this really should be the same here as it is there. Then, let's see, I need to make this thing range from 1 to 101. Okay, now why is that? I want the thing to have a length of 100 just because it's a round number. And I had to have 3 extra points because I'm doing 4-point interpolation. And so 4-point interpolation, the lowest thing that I can deal with is the number 1. And the highest thing that I can deal with is that plus 100, which is 101. So the table itself, since it has 103 things, it nominally goes up to 102, but I can only get up to 1 point less than that if I want to have full 4-point interpolation. This is, putting... It's 103 big. Or is it? Yeah. And maybe I still have the picture. Yeah. So the picture is this. If instead of 3 I had 103, this would go from...
0 and 3 is 104.
But there are 103 points.
Yes,
So it's 0 to 102. So I can go up to 101, which is 1 less than 102. So here, I go from, here there are 4 points, and I can go from 1. It always starts at 1, and where I can go to is 4 minus 2. So 103 minus 2 is 101. Or to put it another way, if I want a usable segment of length n, I have to put n plus 3 points in the table. So I have a usable segment of 100, and therefore a table of 103. And this is very hard to get straight. And I just know it because I had to do it many times. Right. So to make it do that, we'll oops, sorry, wrong button. To do that, we'll multiply it by 100. That's to give it the range, and then we just add 1. And then we tab read it, and we give it the array 3. And then let's look at that. Look at it here instead of that signal. And there it is. All right, so I made an oscillator. Whoopie-doo. Oh, it actually happens to be sort of in phase with the other one, but that's just by accident. And by the way, here's where I didn't get the table to match from end to end, and it will not interpolate from the back end to the front end. It interpolates locally. Right? I'm not going to touch that right now. Okay, so now how to get that to be driven from this oscillator? Well, just use the phase that I got here instead. And now I have phase, and now I have phase-driven table. And now, if I want to... Let's see. Now the situation is I have this thing regardless of what amplitude I put in here. It doesn't change, right? Oh, that's interesting. All right. Cool. I guess I see. It's clipping. Very nice. Okay. Okay, so now it would be totally reasonable to ask for this amplitude to vary with the amplitude there. And of course, there's a dead simple way to do that. All you have to do is multiply this thing by the amplitude, which you get over here. Now, let's see. I'll have to try to make this neater at some point. And now, nothing. Oh, I didn't hook it up. Thank you. Yeah, and now I believe it's the case that if I reduce the amplitude here, I reduce the amplitude there. Right. Okay, so now what I have is an amplitude preserving wave shaping function which will at least take an incoming sinusoid and turn it into any waveform that I want with an amplitude that varies proportionally to the amplitude of the incoming sinusoid. So now you get out your trumpet and get a microphone and blow it into this thing, and your trumpet is playing any waveform that you want. Except a couple of things. One is everyone's going to hear the trumpet. So I'm not sure in the case of a trumpet this is actually going to be a useful wave shaping technique. I use it with a guitar, and it works just great because you can make a guitar not make any sound at all. Let's see. But the other thing about this is that trumpets don't really make sinusoids, and so it's worth actually figuring out what this thing does to a non-sinusoid. And to that end, I've just sort of artificially added another partial, but let me go back to 55 hertz now. It turns out to be a good idea to see what happens when you add the 10th partial to the first partial here. And this is what happens. And this is exactly correct. This is just, there's a word for it. I guess it's a version, it's a sort of Lissajous figure, although it's a rather special one in this case, because the way I'm showing it, I'm making the amplitude of the 55 hertz thing a lot stronger than the amplitude of the 550 hertz one. And notice that I've chosen them to be multiples. If I make this inharmonic, then it won't repeat neatly, and then I'll get stuff like that going on. Oh, that's cool. But anyway, back to 55. Yeah, you can have lots of fun with this. And let me just not have fun with it right now because there's other stuff to do. Okay, so what you can see about this is, I'm gonna leave it looping here so you can see what's going on. If I now graph the result, that's going to be a problem. Well, who knows? We'll see. If I now graph the phase, oh yeah, that's not such a problem. Yeah, look what you get. You get, you get exactly what it looks like you might get. If you think about what the angle is kind of processing a little fast and a little slow and a little fast and a little slow, as if you were watching one of the moons of Jupiter, say. All right. In fact, the Greeks before Kepler came along. It was Kepler. Before Kepler came along, everyone thought that the planets moved in combinations of circles, epicycles. And this is an epicycle. That's exactly how the Greeks calculated planet orbitals. They did Fourier transforms of the orbitals. Avant la lettre. Okay, so what's happening here is it's an epicycle. It, interestingly enough, since it's going 10 times as fast as this, it goes farward. If you count the number of loops here, it's 9, right? Not 10, because the whole thing has gone around once, and so the thing that's gone around it really has only gone around it 9 times in the frame of reference where it thinks the sun is in a fixed spot. Or to put it another way, the moon actually rises one fewer time per year than it does really, because it's, what am I saying? Rises later every day because the Earth's moving around the sun. Right? That's not right what I just told you. Something like that is right. Okay. So anyway, you're seeing that here. You're seeing the fact that you're seeing solar days instead of sidereal days, or something like that. All right. Which discontinuity? Oh, this. Oh, yeah. That's not a discontinuity. That is just the fact that a phase of 1 is the same thing as a phase of 0. So it's just right about at the point where it was here, and then it wiggled backward, but since it's this loop right here, which is actually crossing the horizontal axis, so the phase is some small number there, but it's some large negative number here. But that's not going to matter because this table read, it doesn't because I didn't draw it well, but this thing, if it's an actual periodic function, will give you the same thing down here as it does up there anyway. And so this jump and these 2 other jumps don't matter. Those are inaudible when you've replaced it with a proper waveform. And now the amplitude of the other harmonic then becomes the amount of distortion that you get in this thing, which also becomes the amount of phase distortion you get in this signal. let's drop this down and see if I can actually believe that this is the original signal. Okay, there it is. But then this peak is narrow enough, apparently, that it becomes easy to wiggle past the peak and make the peak, whatever you call it, trifurcate, turn into 3 peaks, forward, backward, and forward. Yeah, there. Oh, actually, another thing's happening, which is more important than that, which is this. 2 things are changing here. One is the phase is getting modulated like that, but the other is that the amplitude is getting modulated too. So here's now the amplitude modulation. Here's the amplitude. Yeah. It should be a sum of 2 sinusoids approximately, and in fact it's a little bit irregular looking. But what's happening is the thing is pushing out and in roughly sinusoidally, actually 90 degrees out of phase from its phase change. So it's changing phase by going forward and backward, but it's also going in and out. And it's going in and out either 90 degrees ahead or 90 degrees behind its changing phase. So you get amplitude modulation and you get phase modulation, and those 2 modulations are 90 degrees out of phase with each other. In fact, let me see if I can make that clearer. So now, where the amplitude is greatest is where the phase is the original phase. Where the phase is pushed forward the most is where the amplitude is not changed, and so on. In other words, this thing, if you think of it as a sinusoid, should be 1/4 cycle after this. Right? Well, it would be cool if you could make them do that, but what would that do here? Or what kind of path would that be? It would have to go outward as it got ahead and then go, I don't know, it would be a sort of a flowery shape instead, or a gear shape instead of the shape that it is. Yeah, I'm not sure how you would do that. I mean, there is a way to do it because these 2 functions are independent of each other. In the sense that you can draw an arc that would make them do whatever you want them to do within reason. Right? So I'm not sure. Actually, it turns out that this particular phase relationship isn't so bad because if you figure it out, this is FM, and FM makes sinusoidal sidebands. This is AM, and AM makes cosine sidebands. And these sine sidebands are actually out of phase with the cosine sidebands and are phased in exactly the right way to make the actual resulting sidebands be in phase. But that would be pages of math for me to show you that. Or it would be one simple observation, which is this. Suppose you took so this is a mess, right? Suppose you just took the x coordinate of this and played it as a signal. What would you get? So that's this. And if you think too hard, it will be, or if you think about it at all, it will be hard. But if you don't think about it, it's easy. 2 sinusoids. Why? Because in fact, this is just an all-pass filter of these 2 sinusoids, so you get 55 and 550 hertz exactly. So if I took this phase and this amplitude, and if I just decided, make me a sinusoid, please, which is this. Again. Well, I'll keep this around, but I'll do something simpler, which is, let's keep the multiplier around. Except I'm going to do something better, which is make it easier to see. But instead of doing this, I'm just going to take the cosine of this thing. All right, so there's the cosine of the angle. Then I'll multiply that by r, and r times the cosine of an angle is just x. So this is an exact reconstruction. Sorry, am I going to make room? So here, if I play this, same sound. In fact, it's not just kind of the same sound, it is so much the same sound that if I subtract these two, I will get silence. Like this. Trigonometric identity. All right, so what did I do? I took here the x value of this, and here I took r times the cosine of theta, and r times the cosine of theta is just x. That is this. I don't know if I need axes or not. I do, yeah. So there's, all right. So here's a point, and here's a, what do we call it, a number, a radius, a distance r. Here's an angle theta. And now if I drop a perpendicular here and ask what is this distance, that is r cosine theta. And here I, let's see, here I'm just grabbing the x value, and here I'm actually computing, oh, sorry, where I'm not showing you that. Here is the x value. Here is the product of r, and this is r, and this is theta, and this is cosine theta. So there's r cosine theta, which is exactly x. And I tried it out by subtracting and hearing nothing. All right, questions about that? Right, so now, for instance, if I wanted to, oh, and what would that sound like? That sounds like this. Oh, no, wait, that sounds like nothing. What I want to do is play r cosine theta, and then you hear this. Good, okay. Now, actually, let me leave that on. And now I'm going to turn this off. Whoops, off like this. And now, okay, so now we're back to the nice, well-behaved situation where we have a nice phase in it. Ooh, why is that changing? That's changing because, no. Yeah, I think I got this frequency so low that the filters aren't quite 90 degrees out of phase, that this isn't quite a circle. And so this is actually gently drifting. Okay, so let's now go give myself a nice reasonable frequency. And now decent frequency means that I have decently constant amplitude. Okay. And now what I'm doing is I'm listening to r cosine theta, but I can always listen to, for instance, where am I going to put all this stuff? I could always listen to r cosine 2 theta. And then I'll get this. So now I've got a frequency doubler. Okay? But the frequency doubler doesn't act the same way when I add the overtone. What? Oh, sorry. Never mind that. I didn't use the overtone. I have to change this frequency before that becomes a reasonable thing to do. There it is. Now, that's interesting. Oh, well, I guess it's right. So, anyway, let's see. I really think I should give myself a range control here because I want to be able to turn this on and off. So let's make the usual divider scene here. Okay, so now second harmonic, and what the second harmonic does. It sounds FM-y, and in fact it is FM-y, because what you're looking at is, well, it's got FM in it. Oh, it's also got AM, but at this point the FM is kind of winning. And to make it a little bit clearer now, I could make this thing be a much lower frequency, like the third harmonic. And now I have kind of an FM sound. But that's just asking for the second harmonic, right? And again, if I ask for the first harmonic by doing this, then I don't, it just miraculously doesn't do that because that's the R cosine theta thing. But the other harmonics that I could add in give me more complicated, well, give me complicated side products if I start asking for stuff like harmonics. Like that. Okay. And now, of course, we can go listen to the result of giving it an arbitrary wavetable like this. Oh, why did that change? Oh, yeah. That's because I'm not doubling the frequency. Okay, very good. So now I have this waveform. Oops. Sorry. Let's listen to it. Oh, yeah. Oh, I do want that multiplier. I'm sorry. Always want to multiply it by the amplitude so it'll shut up when the input goes away. And now I've got, not showing it, now I've got this. Oh yeah, that's with the no harmonics, but then with the harmonic, I get that. Sort of FM, sort of AM, but also wave shape. So now I have lots and lots of whammy bars. So to go back, this table could be one of a bunch of different tables that I would select for whatever reasons that I would want to, or could make linear combinations of. So for instance, if I wanted to, I could make a Hammond organ style drawbar thing to select these harmonics. I could, like, say, cosine of the thing and cosine of twice it and 3 times it and so on. And then give myself controls over, but basically just, make a waveform out of these cosines, and then that would make the it would give me the exact waveform if I just fed it a sinusoid, but then when I fed it something that had harmonics in it, then it would be doing AM and FM on that waveform. And when you do AM or FM on a carrier signal, if the carrier signal is a linear combination of simpler signals, the result is just a superposition of the original things. So FM also is linear in the carrier signal. Linear in the carrier waveform, but not linear in the modulator. So, for instance, you can FM. FM is say phase modulating a bunch of oscillators. You can phase modulate them separately, or you can just phase modulate a single oscillator that has the combined waveforms, and it's the same operation. Right now, what am I not telling you about this that is important to say? Oh, yeah. So this is a good way of thinking about it when it happens that the signal is well behaved. That's to say, when one of the harmonics is, actually the fundamental is much louder than the other harmonics, and then you get reasonable phase behavior. But if you go too crazy with this, you can get phase signals that actually have several cycles in them, like that. So what I've done now is I've made the epicycle so big that it actually wraps around 3 times per cycle, and so suddenly we got a rather radical change in how the thing is going to behave. The good news is that that's actually not a discontinuous change, because right as the thing passes through 0, it's got 0 amplitude, so you don't hear a discontinuity. It's just that the nice theory that we put around the thing which is roughly true when the thing is dominated by the fundamental, is no longer true when you start doing stuff like that to it. All right. Other thing is, when this thing goes inharmonic, nothing is true anymore. And I don't know any good way of thinking about this stuff. At this point, just smoke something and enjoy the pictures. Yeah. I think it's beyond the ability of theory to really deal with that. But of course, it's a perfectly good signal. You can play it out a speaker and it's fine. Questions about what's going on here?
Just for clarity, could you explain that what's unit polar?
Oh, yeah. Okay, so the outputs are, this output is R, which is the distance from the origin, and this output is a phase from 0 to 1.
Right.
So it's R and theta. It's the polar coordinate representation of the sound. Other questions like that?
So why do you need the Hilbert to split it into these two signals?
You need the Hilbert because you can't get the phase. Actually, you can't even get the amplitude, but you sure can. But even more so, you can't get the phase out of the signal until you have it in quadrature, which is to say when you have two copies of the signal that are 90 degrees out of phase. And plus, you wouldn't get the pretty pictures.
You can get the amplitude in the sense that you can just find out what the hottest.
Yeah, if you wait but then you have to wait a cycle, and then how do you know what a cycle is, and so on? It's tough. In practice, it just doesn't work terribly well. What else should I tell you about this? If you want to do this to a real signal, let's go get that guitar thing. Let's see, so we go. Except I think it was like that. All right. Here's a signal. This is pretty lousy, but we can probably deal with it. And why am I multiplying by 5? Well, we'll see. All right, so let's turn this on. See if we're okay. Well, I don't know. Find out if we're okay by listening to it. Nothing. All right, so I guess I've got to go find out what went wrong. So how about the PD window? So it doesn't have any trouble at all. It's happy as a clam. So what is wrong? Maybe my filter hates me. Maybe I have to click this. There it is. All right, this is going to get old really fast. So here's nice, very, what's the right word? Stringently filtered version of the above. Butterworth Shelf 3, this is a filter which you just don't want to get into filter design because you'll lose your life designing filters. But here's a nice Butterworth shelving filter. This one is designed to start tipping off at 500 hertz and then to level back off at 2 kilohertz. And because it's a 3-pole filter, it should then give you 18 dB per octave of separation. So those are 2 octaves separated, so it's actually knocking 36 dB off of 2 kilohertz. And why those 2 numbers, I don't know. That was what was working for some instrument I was trying this with at one point in the past. Why do I care about that? Because let's look at what it looks like as a signal when we throw it through Hilbert and then start graphing it. So our graph is there, and now we're going to look at first off at the original signal. Yeah. And it's just unruly. This is what reality looks like. This is what real music should look like when you graph it. At least when you do the Hilbert transform on it and then look at it. So yeah, you can rationalize this as epicycles around a fundamental, but it doesn't look like the analysis is going to help you much in trying to predict what's going to happen. So the next thing you do then, when you can't predict what's going to happen, is you just do it and find out what happens, right? So right now we have this array hooked up, and it's going to be horrible, right? Now, the good thing about this is that it's amplitude preserving. So I actually, it doesn't give me, what's the right word? I can actually play quiet notes through it and loud notes through it, and it will actually preserve roughly the dynamic what's going in. Or to put it another way, it won't automatically change timbre just from the fact that I put a louder signal through. A louder signal gets the same thing, except it just comes out louder, right? And what'll really sound horrible is this one. Yeah, right. Don't even want to go there, right? But now to just do something reasonable, let's just do the frequency doubling thing. And now we have this. So why did it go away? I've got it going here. I disconnect. Oh, I turned the looper off. Thanks. Yeah. All right. So that is okay. So here's the original for you. Again, making the original back is this, and now I can add a little bit of this. And now I've got basically a Hammond organ drawbar style fuzz generator for guitar. Just to give you a quick idea. Okay. Now, the thing about this is that if you look at what the phase is, it's just, stock market. Actually, not quite. It does have more of a tendency to go up than down. And so you can sort of see, well, what's the cycle of this? I don't know. Frequency? By the way, this is why pitch trackers are hard to make. It's because this is what a real signal looks like when you actually play into the machine. Okay, so it might, just looking at this by eye, it's looking like there are too many high frequencies for this thing to do something reasonable to. So in general, when you have something that has high frequencies going in and do something that tends to double frequencies, you're going to get just raging, I don't know what, paper sound coming out, right? So really what you want to do is, in practice, you want to go reach for this nice Butterworth filter that makes things behave better. And now we have kind of a reasonable collection of timbres. Oh yeah, that's the original. Okay. And now that's a pretty controllable thing. There's one issue remaining, which is this. That filter really wants to depend on the pitch that's going in. Because really what you would like to do is shave off maybe starting about the third harmonic of the sound is where you want to start having the filter roll off, but that depends on the pitch where you want to do that. So if you do this, that's not really doing terribly well, and what you would really want to do is, I don't know what you'd want to do. I think this has to drop. Woo! Drop. Yeah. Oh, wait, that's where it was. Oh, I don't know. That's kind of interesting, but it's not what I wanted. Anyway, oh yeah, so now we have a nice control that we could put on that. Let's see, is this the low? Well, we'll find out. This kind of control. Okay. What this is doing is changing the, okay, there's a Butterworth filter that has It's a shelving filter that has two frequency extremes, and if you drop the place if you drop the roll-off frequency, that has the effect of lowering the high frequencies as well as leveling off, as well as changing where it starts rolling off too, obviously. And so that's the sort of whammy bar that's going on here. What turns out in practice is that if you can manage to pick the 6 strings of a guitar up separately, you can actually set that filter to a sort of a reasonable setting for each of the strings, because each one of them only has a couple of octaves of range. Whereas the guitar as a whole has like a 4-octave range, and there's simply nowhere you can put the filter that makes any sense at all. And also, this is a good thing for monophonic signals. But let's go back to 500 here. Well, I don't know really what I want this to be. Now let's play the nice chord through it. And this will just be who knows what. Which is not... That sounds like something... Well, anyway. That is a radically different sound from, say, what you got when you clipped the thing. But who knows what it is?
Does it matter that they're majored chords that like preserve the overtones?
Yeah, if I put a nice arbitrary chord in there, I don't actually have one handy, but if I did that, then it would just be Armageddon. Yeah. And that's another reason that you would want to just pick the channels up separately if you could, because then you wouldn't have intermodulation between the strings and you could play any kind of chord you wanted to. Yeah.
Did you invent the guitar synthesizer?
No. People were doing those in the 70s. Adrian Ballou had one. That's old stuff. This actually isn't a guitar synthesizer. This is processing the signal of a monophonic instrument, preferably. You can sing through this. By the way, you shouldn't sing through this because because the way the timbre of the human voice works, the good stuff in the timbre of the human voice has something to do with the resonances of the throat, which are regions of frequency, formants. And this thing takes formants and moves them. So if placement of formant is meaningful, then this will destroy meaning. So I don't think anything that, and I'm not even just talking about language. I mean, like phonemes will get destroyed, but even vocal quality, the thing that singers fight to get, it will just be stomped on by this, because they, if you're a singer, you sing something and then you have to raise your palate to get more resonance, blah blah blah, like that. All that stuff is just destroyed when you send it through transformations like this that changes the timbre around. Or actually, to put it another way, the voice is the thing. The voice is the instrument where you're constantly listening to and adjusting the timbre. It's a thing where the focus is timbre and having a wide range of timbres and being able to make them be high quality. So this thing is a thing which allows you to make a wide range of timbral variation on a thing which might not have the same kind of timbral richness to start with. And if you did this to the voice, you would essentially be not able to make use of the skill of the singer, because the things that the singer was working so hard to produce would get changed there anyway. So this is not. So that's not what to try with this. Let's see. Also, presumably it's only going to be of interest for things that are at least in principle kind of periodic. So I don't think I would put a drum through this thing. In fact, I would think twice before I even tried it on a vibraphone or something like that. Right. And well, maybe that's enough to say about that. I think the other instruments are fair game, except that then you get problems with performance as well. I mean, just problems with having the thing make noise in the room, that you have to decide what you're really going to do with the thing. So solid body instruments are a godsend for this kind of work, because you don't have the actual sound of the instrument fighting with the thing that you process it into. But yeah, I need to make something that isn't just an E and an A chord there, so that you can hear the crazy intermodulation that actually really can happen. Okay. Just to, I don't know what, just to show you what's going on here. There's that. I'll give you a quick look at the patch that I use this in. And to do that, I guess I need to save and close this. And go find my copy of the other. Ooh, yeah, this will work, unless it doesn't. Yet, where's my, oh, right, duh. And I say MSP, and then I say rep. Guitar, spec. So this is an actual patch that expects a guitar input, and of course, there's so much crap in this patch that all you have in the front is just going to be controls, right? And one of the things that you can do here is just, you can download this thing, or you can download a version of this thing from the web if you want. It's on my website. There's a test loop here that, if it works, oh yeah, let's turn that off. Do something like through, oh yeah, there it is. All right, turn that off. And my apologies, this is not expert guitar playing. And then you do, ooh, and I'm also, sorry, hang on. Let's go add me some latency. Oh, I've already got 25. All right, and I'm not going to do that because it'll mess me up. All right, well, I'll just hike it up to 40 and just hope for the best. Oh, am I running anything else? Nope. Okay. Sorry, for some reason it's not running in real time today. Okay, so let's, H1 is cosine. Here's harmonic 2, that's cosine double frequency. Oh, and of course, here, this is a good place to do this. There's a filter, and if you ask for more filtering, you can actually get it to where you almost just have the harmonic. Not really. And then third harmonic. And fourth harmonic. So now, Hammond drawbars. Wow. Yeah. And then too much stuff to even start to describe. So, for instance, triangle waves, which are, triangle and triangle / square / sawtooth wave generator, a little bit Buchla-esque. Well, it's, since you got a phase signal, you can just make any waveform you want. So there's a family of triangle-ish waves that you can get. Here's a Prof, phase line format generator. This is something I'm experimenting with that I don't have a good way of explaining. Here's vocal samples. Vocal samples turned into waveforms, so phase bashed so that you can borrow vocal timbres. And this is going to sound bad, but let's turn that on. Where's it's called VOZ? Where did I hide it? What's the number? 17. Huh. It's not what I remember the note. Okay, and then let's ask for automatic. Yeah, sorry, something is maybe my recording process is making my machine hate itself or something like that. So you're not hearing the thing terribly well. But basically, any computer music that you can think of, you can just drive it from the phase and amplitude of an external signal. And this is a decent example of that, I guess. Questions about all this? And this thing is, one of these works in progress that, oh, why don't I turn this off so that the other PD can, how is this working? I'm just realizing there are 2 copies of PD, both of which have audio open. This one then I can get away with telling it I don't need the input device. And maybe that'll fix my problem here. Well, no, it didn't fix it. Yeah, still not working terribly well. Right. Yeah, so download this and play with it if you want. The key is that if you don't mind my little test loop, just turn this thing on and then you can try it without getting a 6-channel guitar of your own. Questions about all this? Or complaints?
So you recorded that with a 6-channel guitar?
Yeah. Yeah, so that's a 6-channel sound file that the thing's playing through itself.
And the really main reason to do that is to just assign different filters, different bandpass filters to each string.
Well, actually, it's just to prevent intermodulation between the strings. So so if you put if you just put something even as simple as a major third into something highly nonlinear like that, you would just get this huge difference tone instead of getting the actual waveform that you want.
Right, so the technique that we were just looking at really only works for a monophonic signal, and it really wants a sinusoid.
Yeah, that's it.
And things that are lower down.
It doesn't have to be low frequency, but it should have primarily fundamental frequency. The fundamental should be the loudest thing in it. Although if not, it just does something else.
How do we find unipolar?
Do what?
How do we find unipolar?
Oh. Well, it depends. I mean, just as a file, just go open. Oh, actually, never mind. It's going to just be in the uploaded files for the seminar, because I'm keeping a copy of all these files. As soon as I sync it, we'll have it. But it's here too somewhere. It's in lib, and all you don't even want to know all the stuff that's in here. But one of them is unipolar. There we are. Here's a tiny detail. If you have, I told you something about this last time, if you have a monophonic signal and if you're able to determine the pitch of it, then you can change its octave. So for instance, let's go back to just the straight sound. Here's an octave up. All that's doing is pitch tracking each of the strings and comb filtering out all the odd harmonics. And then if you want to go down an octave, just ring modulate by a tone that is a half of the fundamental frequency. And then you can take that down 2 octaves if you really want to. Actually, you could take it up 2 octaves if you cared to. And that's something you do without any of this high-tech stuff I was just talking about the unipolar. That you can just do that to any signal you want that you can determine the pitch of. But on a guitar, since there's 6 strings, you better get the strings separately so that you can pitch track them and so that you can apply a separate comb filter tuned to the pitch of each string. Otherwise it won't work.
What is the nutso button?
That's for entertaining oneself. That every single attack chooses a different one of these presets. so on. That one's good with a little bit of whiskey beforehand. It's actually, the idea actually is an extreme distortion of something that George Lewis used to talk about, which is the idea of if you want to improvise with a computer, rather than have the computer sort of support you, it's actually more interesting to have the computer basically try to flout what you're doing. And a good way to do that is to hit a string and just not know what it's going to sound like until you hit it, and then you find out, and then you have to hit the next string, and so on. It's a good way to prevent stasis. Barf. It's precisely what you might think. Let's see. Where is it? It's here somewhere? Yeah. Yeah, sorry, everything is sort of coming out like barf now because I'm having real-time trouble.
But each one of these has its own set of wavetables, like multiple.
Well, actually,
added in some cases.
well, it's actually just reusing the same wavetables in a variety of different ways. Like they're parameterized things like these triangle waves and so on like that, so that you just set the parameters differently to get different kinds of effects coming out. And there is a filter, or rather, a filter per string. So I'm doing a little subtractive stuff too.
I just think that's a way to deal with noisy signals.
Yeah, it's like, what do you do when you put salt in your coffee? You just pour it out and start over. That's not really a good answer.
No, it's a perfectly fine answer.
One thing that you can do if you have I don't know what's the right word. If you don't mind another 20 milliseconds of latency, peak track it, pull out the peaks, do a peak versus noise separation, leave the noise alone, and then use the peaks for whatever process you're doing, and then add them afterward. And then all of the will just come out like it went in, but everything else will get processed. Works with some kinds of sources, not with others, and your mileage may vary. Person that actually invented that idea, Xavier Serra, will be here in 2 weeks speaking. He gave it the name SMS, which is an acronym. But it basically means pick out the sinusoidal components of a sound, and then the rest you just treat it like it's shaped noise. So certain things like granular synthesis work well on noisy signals, and others like Fourier techniques work well on pitch. So just separate it, have 2 chains, and then combine them at the end. But it's dicey. It's fiddly.